The graph shown in this figure illustrates how the respiratory system helps to control blood pH. We have two graphs to look at. Graph A, I'm going to refer to as the stimulus response graph. It shows how the respiratory system responds to a perturbation in arterial blood pH. And then graph B, we'll call a response effect graph. That is, what does that alteration in alveolar ventilation do as far as manifesting a change in the pH of the blood? Let's go to graph A first. Graph A is a plot of percent change in ventilation rate, percent change, as a function of arterial blood pH. A really good way to think about this graph is to look at the dot right here. Normal arterial blood pH is about 7.40. Under those conditions, any signal sent to the brain indicate that blood pH is normal, and there's no resulting change in ventilation rate. And you can see the graph illustrates that. No change in ventilation, 0. What happens if the blood pH starts to drift downward? Well, chemoreceptors will detect that, signals get sent to the medulla, and the outcome is an increase in ventilation rate. And you can see that with the red curve moving upward. It can increase 100, 200, 250, 300% easily. The opposite is true also. If there is an increase in the pH of blood, that's also detected by chemoreceptors, signals sent to the medulla. This time the outcome is the opposite. The medulla is going to cause a decrease in ventilation rate. It's going to drop down to less than it was before. Now we're ready to move to graph B. In graph B, we see, as a function of ventilation rate on the x-axis, the blood pH change. There are no numbers shown on this graph. It's just that we have a dashed line on the y-axis with a plus at this end and a minus at the other end. Let's do the same thing we did in graph A. Let's say that we start with a normal alveolar ventilation rate. With a normal alveolar ventilation rate, we're not releasing CO2 at anything other than the normal rate of activity. So CO2 is being released by the lungs into the atmosphere at basically the same rate that is being produced in metabolism. No accumulation or removal of CO2 means no change in carbonic acid levels. The outcome, no change in blood pH. So right here we're at 0. Now let's just suppose that the respiratory system has been signaled as a response to a lower than normal pH of the blood, shown on the top graph, with an increase in ventilation rate. Well, if ventilation rate goes up, we're basically exhaling into the atmosphere CO2 at a more rapid than normal rate. That means we have less CO2 remaining in the system to produce carbonic acid, and the blood pH is going to start to shift upwards. That makes sense. In response to a low pH challenge, we're ventilating faster, removing CO2 at a more rapid rate, decreasing the potential to produce carbonic acid and shifting the blood pH in the intended direction. The opposite is true as well. If ventilation rate has fallen in response to a alkaline challenge shown up in graph A, if it drops down to half normal or whatever, we're now retaining CO2, producing more carbonic acid, and reducing the blood pH in a negative direction, which would be appropriate.